the right font.
Okay, so last time we started this activity, we were talking about golden ratio. And we were gonna, I had you measure all these different things. Jasmine, you want one of these? Who's the other person? Oh, Elizabeth, she was. Okay, so we have all these numbers and we want to find all these ratios. And we're gonna write down everybody's ratio. We're gonna write it. Let's see, the top of your head is 24. Top of your bun is like 27. Okay, so write your name and then figure out your ratios. So like ratio number 1, the distance from the first measurement you had divided by the second measurement. And these are gonna be decimals. Look around to 3 decimal places. So we're gonna take a little bit of time and do all the measurements if you haven't finished those yet. Jasmine, do you need to measure? Yes. Yeah. This one's easy to measure, like from the ground. It's gonna take us a few minutes to get all these down. So ground divided by top of your head. No, that's right. Yes. Let's do 24.5.
Elizabeth is waiting.
Thank you. Hey, Elizabeth, if you watched the video I sent last time, were you able to open that video?
No.
Okay, I sent the same thing to Jasmine. She said she could, but maybe I sent well, I don't know.
Now, I opened the email as soon as you sent it though, so maybe it just wasn't fully uploaded yet.
Oh, it should be now.
Okay.
So at the end of class last time, we were doing this activity to talk about the golden ratio.
Okay.
We measure all these things and then we're gonna look at the ratios of all of them. So
Okay.
if you don't really necessarily have to do this part, but if you'll give us a few minutes to get all our numbers together, we'll talk about it.
Okay.
So that's what we're doing right now, is just putting all our numbers and figuring out all our ratios right now.
Okay.
My ratios were right.
Four, second, third. 1.1. I said 3 decimals. Oh, that was even. 3, 6, 5 from elbow. So that was it. Okay, so 1.35. That's what I have. Okay, so Brendan, are you done? Did you do all your ratios?
Yes, ma'am.
Okay, what was your first one?
1.483,
483. What was the second one?
1.955,
Okay, 3,
2,
2, 4,
0.667,
0.667, and 5,
1.25.
1.25. Okay, Jerry, are you done?
Yes.
Okay, what'd you get for the first one?
1.692,
Okay, second one,
2,
2, third one,
1.333,
okay, fourth one,
1.5,
and fifth one,
1.414.
okay. Oh my gosh, I don't remember her name. Madison, sorry. Ratio 1.
1.538,
538, okay,
2,
2,
1.8,
8,
1.25,
and
1.385.
385. Okay. Melissa, are you done?
Mm-hmm. One point five two one,
1.521,
2.027,
027. Okay.
1.333.
Okay.
And then 1.5,
1.5,
1.307.
1.307. Jessica, are you done?
Mhm.
What do you have?
1.358,
Okay,
1.846,
okay,
1.286,
okay,
1.4,
okay.
and 1.308.
308. Jasmine, we can leave you off unless you're ready.
I'm not.
Okay. Okay, so everybody else? Yes. Okay, so now we're gonna average all of our ratios together.
Can you zoom in?
Yes. And that's not very neat. Sorry, my pen's fat. 2, 4, 8, 3. Six, 9, 2, 1.538, plus 1.521, plus 1.3 divided by 1, 2, 3, 4, 5, 6. We get 1.537 on this one. This one is 1.998. Third one. One 1.553. Oh, yeah. 1.242. And this one is 1.337. So all of our numbers are in between 1 and 2. This one's kind of high. I wonder if this was the one from the ground to your knees. I wonder like if we would have been more specific on the measurement, like what part of your knee. I don't know, I just said the middle, but what if it was like the top of your knee or something? I wonder if that would be a little different. What's the fourth one? Oh, I don't know why that one would be so low, but remember the number, like the golden ratio here. What's the golden ratio? 1.618. So like that's supposed to be like perfection. Like that's supposed to be like what your eyes see is like perfect symmetry essentially. So there you go. If you have any close to 1.6, you're like perfectly symmetrical in that area. So I don't know, just kind of fun, kind of interesting that the ratio of like the lengths of your fingers and like your height and your arms and stuff are like mathematical essentially.
We were close.
I mean, I'm
Yeah.
pretty perfect. So we started that last time. I don't know. This is just might be a fun thing to do in a classroom, especially in a classroom that you're working on measurement, because measurement is something that you learn by doing. And so this was a lot of different measuring. And you could talk about measuring in, you could measure in inches versus centimeters, and you can even see like what the ratios, how they're different. So this is like, you could deal ratios is a middle school math thing, measurement is a middle school math thing. And then it's just fun to see if you're like perfectly symmetrical. Maybe not in middle school, maybe we shouldn't, maybe like don't shoot for perfectly symmetrical, but just talk about how we all have symmetry. How about that? Instead of having a goal number. I don't know. So there you go. Just a fun little activity to do there. So last time we were talking about Fibonacci numbers, and we're talking about Leonardo of Pisa, and we call him Fibonacci. What are the Fibonacci numbers or the Fibonacci sequence?
Like 1, 2, 3, 5, 8, 13, 21.
Yep, you start off with 1 and 1, and then after that you start adding up the two numbers before it. So 1 + 1 is 2, 1 + 2 is 3, 2 + 3 is 5, 3 + 5 is 8, 5 + 8 is 13, 8 + 13 is 21. Ooh, I don't know why I had such a hard time with that. 13 + 21 is 34, 55, and you can keep on going here, right? What type of sequence is this? You know what the word is, if it depends on the number before it.
Oh,
Starts with R.
Recurring.
Recursive. Good job. This is a recursive sequence, and it has a recursive formula. How would we write the formula for this? And the words is add the 2 before it to get it. Let's say that each number, let's say F because it's Fibonacci. So F sub n is the nth term. So your first term, F sub 1 is 1. F sub 2 is 2. How would I write the nth term? How would you have to write the nth term? Add the two numbers before it. What's the number before the nth term?
n minus 1.
F sub n minus 1 plus,
F n.
yep, F sub n minus 2. That's like your formula for it. And the thing about this formula, you have to tell what the first two terms are. Oh, I did this wrong. The second term is 1. Y'all should have corrected me. Sorry. The second term is 1. It's supposed to be a 1. And also, we have to say this is only true for n is greater than or equal to 3. I can't find the second term that way, or the first term. Obviously, you have to like say the first and second term. Be able to add 2 before it, right? So there's your recursive formula. So this started out as what they call a recreational problem, just for fun, like a funsies problem. And it's actually now one of the most recognized mathematical problems because of a lot of different reasons. So let's talk about why it's such an important problem, or some properties of it. Your book goes into a lot of proofs in this part, and I'm not going into the proofs here. You're welcome. But some properties of the Fibonacci sequence. One property is that consecutive terms. So consecutive. What does consecutive mean?
One after another.
The ones right next to each other are relatively prime. What does relatively prime mean? These aren't all prime numbers. Would you agree? Is 8 a prime number?
No,
No. Is 34 a prime number?
no.
No. So they're not prime numbers, but they're relatively prime.
They're close to prime numbers.
They're prime to each other. It means that the greatest common factor is 1. So for any, the greatest common factor of any F sub n and F sub, how would I write the one next to it?
S of n plus 1 or minus 1?
-1 or +1, right? It doesn't matter which
Yeah.
way you go. -1 or +1, the greatest common factor should be 1, or it is 1. And there's a proof for this, that even though this sequence goes on indefinitely forever, that I have a proof to show no matter what, that one and the one next to it have a greatest common factor of 1. So like pick 2 numbers, 21 and 34. The factors of 21 are 3 and 7. Prime factors of 34 are 17 and 2. There's no GCF there except for 1. 34 and 55, 2 and 17, 5 and 11. No GCF. Okay, so again, we can prove it, but let's spend our time doing it. Okay, so that is a true statement. We also know that the sum
You know what?
of the first n Fibonacci numbers is 2 numbers after it minus 1. So f of n plus 2 minus 1.
Over here. Right here. Oh. It's over here.
So what that says is, let's say n is 5. That means if I add up the
Yeah,
first
don't
5
worry.
numbers, the sum should be f of 7, the 7th number minus 1. Okay, so what are the first 5 numbers? 1 plus 1 plus 2 plus 3 plus 5. And that should equal, what's my 7th number? 13. That should equal 13 minus 1. And you can check it. 5 plus 3 is 8, 8 plus 2 is 10, 10 plus 1 plus 1 is 12. And you can do that with any of them. So it's kind of interesting, and there's proof for that, that proves that. But it's kind of interesting because it's like, if you want to find, let's see, we said this is the 7th, 8th, 9th, 10th, that's the 10th. If you wanted to find the sum of the first 10 numbers, instead of adding up 10 numbers, find 2 more numbers after that and subtract 1. So it's a little easier. Okay, another thing about Fibonacci numbers, and we kind of saw this in the video we watched last time, is that this isn't like a special sequence that's related specific, like we talked about, it came from rabbits. And then we talked about like it's in all these different things in nature. It's not that the rabbits are linked to nature, essentially. The idea is more, this is just a growth pattern. And it's a very specific growth pattern that occurs naturally. And we see it in a lot of places. And I have, so I showed you that video last time. I have a couple more examples to show you of that. Let's see, this one. Let's download that. So plants, we saw the tree thing in the book last time, right? How the branches branch off naturally that way. Numbers of petals and flowers. It's not saying you can't have a 4/8 clover, but most of them are Fibonacci numbers like 3, 5, 8, 13. Sections of fruit tend to be Fibonacci numbers. We'll come back to this whole spiral idea because that's related to Fibonacci numbers, but we're not there yet. And then we just did an activity with like your the segments of your fingers. Maybe if we had x-rays, maybe our numbers would be better, right? Like our measurements would be better and our numbers would be better. But the symmetry and different things here. Okay. So that's different applications of the Fibonacci sequence. Another thing about it is the ratios. We did this a little bit ago. Last time we divided each number in the Fibonacci sequence by the one before it, and the ratios approach the golden ratio. And we just said that number was 1.618. That's the rounded number for that. The actual, and there's like a way to get this by making a quadratic and solving the quadratic equation, but the actual number is 1 plus the square root of 5 divided by 2. That's the golden ratio, which approximates to 1.618. And then the last thing we saw in that video was the information about the golden rectangle. They kept on talking about the golden rectangle, and it kind of showed like word where it like moved the rectangle and made the different shapes or the different sizes of it. We're going to do a little activity. We're going to make our own golden rectangle. So the golden rectangle, you're welcome, has, so Elizabeth Marco, I'm giving graph paper. We just wanted to have rectangles that are measured to certain sizes. But we are going to create our own version of the golden rectangle, or our own golden rectangles. And so we are going to start off with, we're doing our Fibonacci numbers here. I don't know if you want different colors here. I have matte pencils. Yeah, it's probably best if you do different colors. You need like, let's see how many different colors we need. 1, 2, 3, 4, 5, 6 to 7 different colors. What's that right here? If you want to, or you do your own, or whatever. Just easier to see with different colors. One, 2, 3, 4, 5, 6, and 7. You can use your pencils one of them though. You need to. So you're going to turn your graph paper sideways. And we want to pick one of your colors, and you want to draw a rectangle that's 2 by 1. And we're going to like pick a spot kind of in this area. Our thing's going to end up being this big. So this area-ish. I'm going to do it right here. There's room to move around. But we're just going to draw a rectangle that's 2 by 1. This is actually 2 different squares. The area of one of the squares is 1. The area of the second square is 1. Okay, and that's like the 1 and the 1 of our Fibonacci sequence. So the next one, we're going to draw a square with sides of 2. We're going to draw it above that one. And our lengths here, 1 plus 2 equals 3 would be our next size up. So we're going to draw that to the right there. So 3x3 square. Oh, dang it. Oh, well, that's fine. I was trying to make it bigger than the initial, I was trying to make it one more step past it. The one I did on my paper, we should have started on the other side of the paper. It's fine. We're already here, so. Okay, so now I already did 1 + 1 is 2, 1 + 2 is 3. Now I need to do 3 + 2. So 3 + 2 would be this length 3 plus this length 2. So this length right here, and we're gonna go 5 down, 1, 2, 3, 4, 5. What size is the next one gonna be? 8. 3 + 5 is 8. And so here's my 5 over here, and my 3 would be 1 + 2. So 1, 2, 3, 4, 5, 6, 7, 8. 7, 8. Sorry, you can't see very good, but out this way to the left. What would the next one be? 13. 13, and that's gonna be up above it. On top. 1, 2, 3, 6, 7, 8. 13. Ideally, if I would have drawn it on the other side of the paper, we could have been drawn one more over here. But it's great. Okay, I'm about to show you the spiral. Finish drawing that. Okay, so for your spiral, we're gonna start at the top right-hand corner of the first one you drew. And we are going to spiral around. We're gonna come down to the bottom and come back through the other corner, other top corner. And then we're gonna come around through your next one. So it's like we're going from corner to corner. And we're not making a straight line, or it's not gonna come out as a spiral. Okay, so we're starting at the corner of your 3x3 box and coming up around to the other corner. Same thing with your 5x5 box. Start at that bottom corner if you're moving your paper around and come up to the top corner. Do the same, keep on going. If you just keep on flipping your paper around, you should just be going from corner to corner. What?
Just fine.
Okay, so this spiral, what did you do? What'd you do?
I messed up.
I was gonna help you.
I was getting,
Can I help you?
I was getting confused because I went this way and it didn't work, and then I went this way and it didn't work.
You did it right. Oh. You have these to switch. Here, to fix it, you make this be your 2x1 and that be that one, then it'll work. Here, you can have mine because I made another one, a practice one before I came in. I didn't want to do this. There you go. Okay, so this spiral is made from your golden rectangles. Again, it would keep on going both directions, right? I could make this is 13 plus 8, 21. I could make a 21 by 21 box over here and keep on going that way. Or you could technically get infinitely small here, as small as you can draw it. Okay, so that spiral is another thing that is seen in nature. Let me find my little PowerPoint. So that's this pine cones, dahlias is your spiral there. But also we see, oh, here's like, you know, your picture, and we saw the rectangles there, but it generates the spiral. And here's places you see your spiral in your hurricanes, solar system, cornucopia. I don't know if that's a thing that occurs in nature, but your nautilus. Okay, so this is naturally occurring things that you can see different ways. And again, that's something that might be somewhat fun. Okay, so now we're going to start. So that's essentially your properties that you see in the Fibonacci sequence. You can do lots of different things with it. There are lots of more properties and lots of more problems that you can prove. We are going to stop at that level though. So on that note, there is this problem, this math problem. It's called the 3x plus 1 problem. And this is a currently unsolved math problem that is super duper simple, but it has not been proven thus far in the past. Hundreds and hundreds and hundreds of years. Okay, so the 3x plus 1 problem says, basically, we're going to pick a number. If your number's odd, we're going to multiply by 3 and add 1. If it's even, we're going to divide by 2. And we're just going to keep on going with whatever your answer is. So the mathy way to write that would be a piecewise function. And your piecewise function would say, whatever you have, if it's even, you divide by 2. So it would be x divided by 2 if x is even. And you do 3x plus 1 if x is odd. And whatever your answer is, you plug it back in. You keep on going over and over and over and over. Okay, so we're going to do a couple numbers here. And then we're going to kind of talk about what we think is going to happen and talk about like how you do proof of it. And then I found a video that was fascinating. Actually, got to that video from looking at another video for something we're about to learn after this, but it was fascinating. It gets a little mathy, but I feel like there's things throughout it that are important to watch the whole thing. So we're gonna watch the whole video. But let's do a few numbers. Let's start off with x equals 4. So if you have the number 4, is 4 even or is 4 odd? Even, so you divide by 2. So 4 divided by 2 equals 2. Is 2 even or is 2 odd? Even. So I do 2 divided by 2 and I get 1. Is 1 even or is 1 odd? Neither.
Well,
Yeah.
it's odd. It's odd.
It's odd.
I thought we were told it's neither
Yeah.
even or an odd. One of our classes told us that.
Who told you this?
I don't remember, but I remember being told it was technically neither,
Yeah.
just like 0.
Oh, here's the I got all the reasons why. It's odd. First of all, the definition of an odd number is it's 2 times n plus 1, where n is an integer. So let's pick the number 0 for n. 2 times 0 plus 1 is 1, right? So it's an odd number. If you want to go back to kindergarten, in kindergarten, your definition of an odd number, do you know what the definition is in kindergarten?
It can be divided by 2.
For a kindergartner?
Oh, wow.
Because my son came over in kindergarten and said he learned about even and odd numbers, and I was like, what do you mean you learned about even and odd numbers? So that's what I thought. Do you know how they teach it in kindergarten?
No.
Even numbers, everybody has a partner. Odd numbers, one person doesn't have a partner.
Oh, and they split up the number?
Isn't that the cutest thing? So does one have a partner?
No.
It's odd.
I mean, I always thought it was odd, and then we got told it
Right?
wasn't, so.
I'm gonna need y'all to think about it. Who told you
Wow.
this?
Me too. I'm not thinking.
I mean, do I not know something?
I'm gonna go back and look.
This is the definition of an even number. I'm sorry, of an odd number. It's 2 times n plus 1. An even number is 2 times n.
You want this back?
In a minute. Okay, so anyways, we get to 1. Is 1 odd?
Yes.
Yes. So I do, thank you, good job, guys. So I do 3 times 1 plus 1, because 3 times x plus 1. And what do you get? 4. And it's this like infinite
Wait a
loop.
minute. Go back where we started.
I know. So we're gonna be in this loop. So the interesting thing about this problem is we think every single number gets to this loop and gets down to 1. And once you're back at 1, you go back to this loop over and over and over. So let's pick a different number. And some of these numbers take a lot longer to get to that loop than others. So we're gonna be a little picky about our numbers. We're gonna pick the number 6. I'm looking up, is 1 odd now?
We didn't mean to confuse you,
Yeah.
but I
Are you
thought
talking
I
about-
wasn't the only one.
I thought that too. I thought.
Yeah, it's odd for sure. Are you thinking that 0 is not positive or negative?
No, it was.
No,
said
it
no.
was 1,
I'm gonna need y'all.
because I was shook when we were told. I was like,
I'm gonna need you to figure out who told you that, and so I can go try to have a conversation with that person. So maybe I don't know, but Google says it, my definition says it, kindergarten says it. Everything says it.
kindergarten says it.
Okay, so if I do 6, so I start off with the number 6. Is 6 odd or even?
Even.
Even, so I do 6 divided by 2 and get 3. Is 3 odd or even? Odd, so 3 times 3 plus 1 is 9 plus 1, which is 10. Is 10 odd or even? Even, so I do 10 divided by 5 equals 2. Nope, backwards, 10 divided by 2 equals 5. What's funny is when I worked this out, I did the same exact thing and I had to erase it and do it right. It's 5, is 5 odd or even? Odd. 5 times 3, nope, 3 plus 1, 15 plus 1 is 16. And 16 odd or even? Even. 16 divided by 2 is 8. Is 8 odd or even? Even. 8 divided by 2 is 4. We've made the loop. 4 divided by 2 is 2. 2 divided by 2 is 1. And we end there because we would go back to 4 and do that loop forever and ever and ever. So the problem states that if you follow this rules, this piecewise function, and keep on plugging it in, every single number should get down to 1. Okay, so it's not a difficult problem, right? Like this isn't like we're doing like super hard math or anything. So think about how you would try to prove this problem. So usually this has not been proved, so we are not going to sit here and attempt this today. But usually when you try to prove something, you look at like the properties of a number and you see if you can like, you know, make things cancel out or that sort of thing with the proofs. Because like you can prove infinite things is true. For example, we can prove that any 2 terms in this infinite sequence have a greatest common factor of 1. Like that is, it's only like a, well, I'll show you the proof. It's in the book. It's not even that long. Let me pull it up. Here's the proof of that. It's just right here. Like, just if you lines worth of proof, essentially. Okay, so it's not hard to prove that. You can prove that we did on your test, the sum of the first n integers is n divided by 2 times n plus 1. Like that's an infinite proof. You can prove infinity things like can have a pattern or whatever. But this one has not been proved and cannot be proved up to this point. So I'm gonna let you watch this video. This video is a little bit long. It gets a little mathy. And I was trying to figure out a point where I was just gonna cut it off and say, that's too much. But it just kept on coming back to things that were important. Like it would come out of the mathy stuff and apply it to something else. So this problem applies to a lot of different things in real life. So that's why I wanted to, that's why I showed to you. So this one.
What's it like to learn math on Brilliant.org? Brilliant gets you hands-on to help you learn by doing. This is the most dangerous problem in mathematics, one that young mathematicians are warned not to waste their time on. It's a simple conjecture that not even the world's best mathematicians have been able to solve. Paul Erdős, a famous mathematician, said, "Mathematics is not yet ripe enough for such questions." Here's how it works. Pick a number, any number. 7, good choice. Okay, we're gonna apply 2 rules. If the number is odd, we multiply by 3 and add 1. So 3 times 7 is 21, plus 1 is 22. If the number is even, we divide by 2. So 22 divided by 2 is 11. Now we keep applying these 2 rules. 11 is odd, so we multiply by 3, 33, and add 1, 34. Even, divide by 2, 17. Odd, multiply by 3, 51, add 1, 52. Even, divide by 2, 26. Still even, divide by 2, 13. Odd, so we multiply by 3, 39, add 1, and that's 40, which is even. So we divide by 2, 20, divide by 2, 10, divide by 2, 5. Odd, multiply by 3, 15, add 1, 16, divide by 2, that's 8, and then 4, 2, and 1. Now 1 is odd, so we multiply by 3 and add 1, which equals 4. But 4 goes to 2, goes to 1, so we're in a loop, and the lowest number is 1. Now the conjecture is this. Every positive integer, if you apply these rules, will eventually end up in the 4, 2, 1 loop. This is commonly called the Collatz conjecture after German mathematician Lothar Collatz, who may have come up with it in the 1930s. But the problem has many origin stories and many names. It's also known as the Ulam conjecture, Kakutani's problem, Thwaites conjecture, Haas's algorithm, the Syracuse problem, and simply 3n plus 1. Why is 3x plus 1 so famous?
Among professional mathematicians, maybe it's not famous, but infamous. In the sense that if someone actually admits in public that they're working on it, then there's something wrong with it.
The numbers you get by applying 3x plus 1 are called hailstone numbers because they go up and down like hailstones in a thundercloud, but eventually they all fall down to 1, or at least we think they do. You can think of the numbers as representing the height above the ground in meters. So a number like 26 would start 26 meters above the ground. And if you apply 3x plus 1, it rises up as high as 40 meters. And in total, it takes 10 steps to get to 1. So 10 is called its total stopping time. But take the very next number, 27, and it bounces around all over the place. In fact, it climbs all the way up to 9,232. As an altitude, that is higher than Mount Everest, before it too falls back to the ground. In total, it takes 111 steps from 27 to get down to 1 and end up in the 4, 2, 1 loop. The paths that different numbers take vary so widely, even numbers right next to each other. So how do you even start to make progress on this problem? Well, honestly, mathematicians struggled.
People just decided that this was something invented by the Soviets to slow down US science, and it was doing a good job at it because everybody's sitting there twiddling their thumbs and making no progress on this trivial thing that you can tell school children.
Geoffrey Ligarius is the world authority on 3x plus 1.
The first time I met him, I was a senior in college, and he pulled me aside and he said, "Don't do this. Don't work on this problem. If you want to have a career, do not start spending time writing about this or publishing any papers about this, do real math for a while to establish yourself.
Alex Kontorovich didn't listen. He and Yakov Sinai looked at the paths of the hailstone numbers. Were there any patterns? Well, obviously all of them end up at 1, but what about the paths they take to get there? The pattern is randomness. Here is the sequence of a large number chosen at random. The graph peaks and then drops so low that you can't really see what's happening at this scale. But if you take the logarithm, you find this wiggly graph with a downward trend. It looks kind of like the stock market on a bad day. And this is no coincidence. Both are examples of geometric Brownian motion. That means if you take the log and remove the linear trend, the fluctuations are random. It's like flipping a coin each step. If the coin is heads, the line goes up. Tails, it goes down. 3x plus 1 is just like the random wiggles of the stock market. Over long enough periods, the stock market tends to trend upwards, while 3x plus 1 trends down. Another way to analyze 3x plus 1 is by looking at the leading digit of each number in a sequence. Here are the hailstone numbers starting with 3 as the seed. And we can count up how many numbers start with a 1, how many start with a 2, how many start with a 3, and so on to make a histogram. We can do the same thing for the sequence that starts with 4, that's a short one, and for the sequences that start with 5, 6, and 7. Again, for each sequence, we're just counting up how many numbers start with each digit, 1 through 9, and adding that to our histogram. If you keep doing this for more and more numbers, eventually the histogram settles into a stable pattern. For the first billion sequences, you'll find 1 is by far the most common leading digit. 30% of all numbers start with 1. Around 17.5% start with 2, 12% start with 3, and the frequency decreases for higher digits. Fewer than 5% of all the numbers start with 9. Now this pattern is not unique to 3x plus 1. It actually comes up everywhere, from the populations of countries to the value of companies, all the physical constants and the Fibonacci numbers, just to name a few. The distribution is known as Benford's law. And it is even used to detect fraud. If all the numbers on your income tax forms obey Benford's law, then, well, you're probably being honest. If not, you may be hiding something. In elections, Benford's law can be used to spot irregularities, though you have to apply it correctly. Benford's law works best when the numbers involved span several orders of magnitude, as they do for 3x plus 1. But Benford's law can't tell us whether all numbers will end up in the 4-to-1 loop or not. For that, we need a different sort of analysis. At first glance, it seems strange that when you apply 3x plus 1, all numbers should end up at 1. I mean, consider that there are the same number of odd and even numbers, but odd numbers are more than tripled, while even numbers are only cut in half. Therefore, it seems like every sequence on average should grow, not shrink. But here's the catch. Every time you multiply an odd number by 3 and then add 1, it will always become an even number. And that means the next step is to divide by 2. So odd numbers are not actually tripled by 3x plus 1, they're increased by a factor of about 3/2. I'm neglecting the plus 1 because it's insignificant for large numbers. And 3/2 is actually the most an odd number can grow in one step. Think of the path from one odd number in a sequence to the next odd number. After multiplying by 3 and adding 1, you have an even number. And 50% of the time, dividing by 2 brings you back to an odd number. But a quarter of the time, you can divide by 4 before you get to the next odd number. So for a quarter of numbers, the next one in the sequence will be 3/4 of its initial value. An eighth of the time, you can divide by 8 before getting to the next odd number. And a 16th of the time, you can divide by 16, and so on. If you take the geometric mean, you find on average to get from one odd number to the next one, you multiply by 3/4, which is less than 1. So statistically speaking, 3x plus 1 sequences are more likely to shrink than grow. Take 341, for example. Multiply by 3 and add 1, you get 1024, which you can divide by 2, and then divide by 2 again, and again, and again, and again, 10 times in total until you're down to 1. One way to visualize these paths of numbers in 3x plus 1 is simply to show how each number connects to the next one in its sequence. This is called a directed graph. It looks like a tree or a series of little streams that flow into each other. If the conjecture is true, it means that every single number is connected to this graph. Every tiny stream all the way out to infinity eventually flows into the massive river of 4, 2, 1. Some mathematicians have modified this visualization by rotating the graph at each number, anti-clockwise if it's an odd number and clockwise if it's even. And then you end up with a structure that looks like a coral or seaweed. And by adjusting the degree of rotation for odd and even numbers, you can create these beautiful organic looking shapes. Now, there are two ways the conjecture could be false. There could be a number somewhere, some seed, that starts a sequence of numbers that grows to infinity. For whatever reason, it doesn't obey the same numerical gravity as all of the other numbers. Another possibility is there exists a sequence of numbers that forms a closed loop. All the numbers in this loop would be unconnected to the main graph. But thus far, no loop or sequence that shoots off to infinity has been found. And not for lack of trying. Mathematicians have tested by brute force every single number up to 2 to the 68. That's 295 quintillion, 147 quadrillion, 905 trillion, 179 billion, 352 million, 825,856 numbers. We know for certain that every single one of those numbers eventually comes back down to 1. We have tested nearly 300 quintillion numbers, and none of them disproves the conjecture. In fact, given this information, mathematicians calculate that any loop other than 421 must be at least 186 billion numbers long. So it seems pretty likely that the conjecture is true, but this doesn't prove it. One way mathematicians have attempted to prove it is by making a scatter plot with all the seed numbers on the x-axis and a number from each seed's sequence on the y-axis. Now, if you can show that in every 3x plus 1 sequence, there is a number that is smaller than the original seed, well, then you have proven the Collatz conjecture. Because whatever number you pick, you know it will at some point get smaller. And that smaller number as a seed also gets smaller, and so on down to 1. Meaning the only way any sequence can end is in the 4, 2, 1 loop. This has not yet been shown. But in 1976, Riho Terras was able to show that almost all Collatz sequences reach a point below their initial value. In 1979, this limit was reduced with almost all numbers going to less than x to the power of 0.869. And then in 1994, it was further lowered to less than x to the power of 0.7925. In this case, the term almost all numbers has a technical mathematical definition. It means that as the numbers you're looking at go to infinity, the fraction that end up under the curve goes to 1. Then in 2019, one of the world's greatest living mathematicians, Terry Tao, was able to show 3x plus 1 obeys even stricter criteria. He showed almost all numbers will end up smaller than any arbitrary function f of x, so long as that function goes to infinity as x goes to infinity.
Forget Matthew again.
But the
sorry.
function
Give it a
can
minute.
rise as slowly as you like. So log x is an example, or log x works too, or log x. What this means is for almost all numbers, you can guarantee that there is an arbitrarily small number somewhere in its sequence. In a public talk he gave in 2020, Terry Tao said, "This is about as close as one can get to the Collatz conjecture without actually solving it." This is an impressive result, but it's still not a proof. So why can't we prove the conjecture true? Could it be because it's not true? I mean, everyone is trying to prove it true, which means almost no one is looking for counterexamples.
It happened to me just 2 years ago, where there was something I was trying to prove that I was trying for 3 years to prove, and I couldn't get it to work. And then I found a counterexample, and then I realized what the correct statement should have been, and then a month later I proved the correct statement. Maybe we should be spending more energy looking for counterexamples than we're currently spending.
I mean, remember how the number 27 grows all the way to 9,232? Here is a plot of seed numbers up to 10,000, with the largest number reached for each seed plotted on the y-axis. The y-axis stops at 100,000, but not all numbers can be shown at this scale. The seed 9,663, for example, climbs as high as 27 million. And as yet, no one has proven why a number couldn't just shoot off to infinity. And it would take only one to disprove the conjecture. Or some set of numbers could be part of a loop, not connected to the main graph. As far as we know, there is only one loop, 4, 2, 1. But something strange happens if you include negative numbers. Applying the same 3x plus 1 rules as before, there is not one loop, not two loops, but 3 independent loops of numbers. And they start at low values like -17 and -5. Why should there be disconnected loops on the negative side of the number line, but not on the positive side? Now, one of the most convincing pieces of evidence supporting the conjecture is Kerry Tao's proof that almost all numbers have a number in their sequence that is arbitrarily small. But proving that almost all numbers obey this criteria isn't the same thing as proving that all numbers do. How many numbers between 1 and 100 are perfect squares? The answer is 10. So 10% of numbers up to 100 are perfect squares. How many numbers between 1 and 1,000 are perfect squares? The answer is 31. So only 3.1% of the numbers up to 1,000 are perfect squares. And the higher you go, the smaller this percentage becomes, such that in the limit, you could say almost all numbers are not perfect squares. The fraction of numbers that are not perfect squares goes to 1 as x goes to infinity. And yet we know there are an infinite number of perfect squares, and we know exactly where they are. Now, we've tested by brute force all numbers up to 2 to the 68, and they all obey the Collatz conjecture. And you might be thinking that, well, we should have found a counterexample by this point. But on the scale of all numbers, 2 to the 68 is nothing. I mean, the Polya conjecture, proposed in 1919 by George Polya, asserted that the majority of natural numbers up to any given number have an odd number of prime factors. The conjecture was eventually proven false by C. Brian Hasselgrove in 1958, when he identified a counterexample. What's remarkable is the value of this counterexample was 1.845 times 10 to the 361. That's some 10 to the 340 times bigger than all the numbers checked for 3x plus 1. One way to think about 3x plus 1 is as though it's a simple program run on a Turing machine. The seed number is the input to the machine. So in this picture, 2 to the 68 is simply an input tape 68 squares long. You can think of them as a string of ones and zeros or black and white squares. Saying that the machine has transformed every input up to this 68 square tape down to 1 should not give you a lot of confidence that it will do so for all inputs. In fact, it's fairly simple to calculate a number that shows any arbitrary behavior you like, so long as it is finite. If you want a number that increases by 3/2 5 consecutive times, you can calculate that number. If you want a number that climbs by 3/2 10 times in a row, or 100 times, or 1,000 times, you can easily calculate those numbers. But after the finite section you specify, you have no more control, and every number that has ever been tested always falls to 1. If there is a counterexample, it's virtually impossible that someone's going to guess it. And the space of all possibilities is too big to search exhaustively by brute force.
2 to the 1,000 is not a searchable space. So if we're going to find it, we have to find it by some intelligent process and not by guess and check. I had been on team 3x plus 1 for 20 years. And then this point of view, I realized that, like, what do we really know? What? It's very hard to prove a theorem that's false. And so could it be that everyone's struggling to prove this thing because it's not actually true? And 2 to the 60 is not a lot of evidence. And even the statistical version is maybe true and not evidence for the non-existence of a divergent trajectory somewhere in the 3x plus 1 sequence.
Of course, there is another option, and that is that we'll never know, that the problem is undecidable. In 1987, John Conway created a generalization of 3x plus 1. It was a mathematical machine that he called Fractran. And he was able to show this machine is Turing complete, which means it can do anything a modern computer can do. But it also means that it's subject to the halting problem, a chance that the machine never stops running and so doesn't give you an output. And this does not prove that 3x plus 1 is also subject to the halting problem, but it is possible that given what we know, we may never prove the Collatz conjecture true or false.
You're gonna be taught in school that we know a bunch of stuff, and it's a lot. There are a lot.
Like, one is not.
Here's this stupid little problem. Come on. Really, we can't solve this? Really? You know, it just shows it's hard. If anything, it shows that all the things that we can solve are miracles. We have no right to have solutions to all these other problems.
For my whole life, I've thought of numbers as these incredibly regular things full of patterns, symmetry, and repetition. But what I'm realizing only now is just how peculiar numbers really are. You can see this most clearly in the choral representation. From a simple mathematical operation comes something intricate, organic looking, and thus far intractable to us. Do all numbers connect to this structure? Or is there some unique filament, a spindly little thread that doesn't connect to any of this, that runs off to infinity? And why is it so hard to tell? I think that's why Paul Erdős said, mathematics is not yet ripe enough for such questions.
Is that interesting?
What I love about 3x
That's just, he's telling you to subscribe to whatever is paying for it at the moment. Is that kind of interesting?
Yeah.
Like, it's like a super duper simple problem. Like, it's not hard to do, but it's like, you can't prove it. I hope that kind of relates back to geometry with all our proofs and stuff. So, sorry, moving on. That was just a little, so how that connects to the Fibonacci sequence is if you change that problem to x plus 1, you can basically do some proofs with it that come down to the Fibonacci sequence. So that's why it's like included in this part of the set. Okay, so we're going to spend just a couple minutes prepping for our next section. We're going to do the introduction to the section. The next thing we're going to talk about is the cubic controversy, and it's super dramatic and it's really fun. So let's kind of like move in that direction. So the cubic controversy, we got to get from where we're at with Fibonacci. So Fibonacci is time periods like 12 something, 1200. Fibonacci's dates are, let me see, 1175 to 1250. So we're like 1250-ish time period, 1200 time period-ish. Okay, so like things that are going on worldwide is around the 1300s. 1300s is the beginning of the Ottoman Empire. And that is important because in 1453, they take over Constantinople. So it's the fall of Constantinople. And do you remember what that is? Constantinople is? It was like the capital city where the House of Wisdom was. And this is where we're like translating all the Greek works into Arabic and doing all that stuff. Okay, so the fall of this. So all of the works, like this is where all the works are located at the time, because they've been translated and rewritten, and all the ones before this have probably like disintegrated at that point. So all that, and we'd already talked about a little bit last time about works being brought over to Europe. But at this point, a bunch of refugees bring over all the works. And when I talk about the works, not just math works, like Plato's works, like all the works from the Greek time period to Italy. And this is where they're translated now from Arabic to Latin. Okay, and we kind of talked about this process was already started a little bit. So from Arabic to Latin. But during this time, something really, really important happened that made translation progress very, very quickly. And it was the invention of the printing press. The printing press was invented in 1440. So instead of having to copy by hand everything, we're starting to print things. Okay. So this is a big deal because instead of mathematicians spending time translating works and reading old works and rewriting them over and over, we're now able to focus on moving forward and the progress of mathematics. Okay. So during this time period, one thing that they had was they're called like mathematical, or no, they're called academic contests. And I like to refer them to mathematical duels because that's kind of what it reminds me of. Okay, so during this time period, all your scholars are like dueling other scholars essentially in terms of problems. And the way this happened is, well, first of all, the reason why this happened is think back to the House of Wisdom and at Alexandria, the Academy, all these scholars were able to just like do math and teach math and study math because they were paid, right? They lived there, their food was provided for, everything was provided for them, and they didn't have to make a living. So they were able to like just devote all their time into research and learning new mathematics. Okay, so that's not the case anymore. We don't like both of those places have fallen. So at this point, they still have to make money. So the way they're making money is by being teachers, and to be a teacher and make money, you have to have students following you. So these contests gave you a little bit of fame, and it's like, well, if this person won that contest or won that duel, essentially, then I should be, if I want to be a math student, I should be this study under the person who won and not the person who lost. So that's the idea was these contests are for notoriety, fame, and money, essentially. And there's rules to these contests also. The rules say that you're not allowed to pose problems to somebody unless you've already solved the problem. So you can't just like pose the 3x + 1 controversy and say whatever. It's like you have to have the solution to it. And so there's like all these different rules. Usually there's a prize for the winner. I think in the one we're going to talk about, the prize was like 30 dinners or something like that was going to be provided by the loser. So there's prizes, but also whoever wins gets the fame and notoriety. Whoever loses looks like you're not very smart, doesn't know what you're doing, and then students don't want to study under you and you can't make a living. So we're not actually shooting guns at the duel and killing people, but essentially like your living is being shot at that point, right? So that's the idea of this time period. The bad thing about this is if you discover new mathematics, are you going to go tell the world about your new mathematics you discovered? No, you're going to propose a problem to somebody who doesn't know that new mathematics and get the fame out of it, and you don't ever have to provide a solution like once you do that. So that was kind of the thing, is like this kind of started turning back into like Pythagorean stuff of like discovering all these mathematics and keeping it a secret and not telling anybody, because then you have job security because nobody else knows how to do it. Okay, so we are going to stop there, but that sets the stage for the next time. We're going to talk about the cubic controversy, and it is very dramatic. Controversy, yeah. And the cubic controversy is the solution to any cubic equation. So degree 3 x to the 3rd power equation, because we already have the quadratic solution of this one. So we will pick up there next time. Next week, I know we haven't done, I'm not getting a lot of homework, but I can't imagine y'all are mad about that, but there's not like what would I do? We do homework over this? Go solve the 3x + 1 problem? Like that's not an option, right? So we are going to have another project. I'll have that ready next week of like topics, kind of like you did your person. You're going to pick a topic. So if anything's interesting to you, maybe if one is an odd number, maybe that's an interesting topic to cover. No, don't, oh. So, if you have any topics, be thinking about that and you kind of start researching that, I'll give you the details for that next week. I'll probably also give you the details for kind of the rest of the semester next week of like what we're gonna go over, dates, all that kind of stuff, so. We'll have one more test and then the finals option. I'll tell you what, I can say right now, when the next test will be. Let me see. You gotta work backwards from final exam. So final exam is this week right here, 9th through 13th. So if you're taking final, that'll be it. This is study is the end of that week. So the beginning of that week will be final exam review if you're taking the final exam. So your test will be either April 26th or April 28th.
Or the 21st.
Yeah, I mean, if we do the presentations after the test, it'll be either the 26th or the 21st. If we do them before the test, I'll map it out and plan it out. It basically, that'll depend on when I give you the projects. I'm gonna give you time to do the projects, so on and so forth. So the end of April, the last 2 weeks of April. Okay, I will tell you right now, we will not have class on April 14th because I'm going on a field trip with my son's 3rd grade class. We're going to see The Lion, the Witch, and the Wardrobe at the Dallas Children's Theater or something. So we will not have class on the 14th. I don't think I can get, I'll be back by then. Yay. Okay, so I'll give you all that information next time and I will see you on Tuesday.
You and Boucher should do
Boucher?
it all.
He'll win every time.
No, you would win.
No.
Because he wouldn't.
Wait, stop. Let me stop recording this. Stop.